On June 3, 1997, Brazilian defender Roberto Carlos struck a free kick from 35 meters out. The ball initially cleared the wall of defenders by a wide margin, appearing to head out of bounds. Then, in the final milliseconds of flight, it bent sharply inward, hooking into the net. On the opposite end of the kinematic spectrum is the knuckleball. When struck with near-zero spin, a soccer ball travels in a highly erratic zigzag pattern, abruptly changing direction mid-air and leaving goalkeepers unable to predict its final destination. These movements often appear to defy logic, yet they operate strictly within the laws of physics. These trajectories are predictable physical responses to specific launch conditions. When speed, spin, and surface texture align, the air is forced into distinct flow patterns that dictate exactly where the ball must go. When a player kicks a ball, they impart two primary kinetic vectors. The first is translational velocity, the speed the ball moves forward. The second is angular velocity, the rate it spins. As it travels, it interacts with a third variable, the boundary layer, a thin region of air dictating fluid flow. To understand the engineering of modern soccer balls, we have to mathematically model how extreme variations in these three variables produce these paths. We start with high spin and the Magnus effect. As a spinning ball moves through the air, it creates an asymmetry in the flow separation. This pressure difference generates a steady lateral force, pushing the ball perpendicular to its forward motion. The intensity of this lateral push is governed by the dimensionless spin number. This is calculated by multiplying the ball's radius by its angular velocity and dividing that by its forward translational velocity. It represents the precise ratio between rotation and forward speed. For Roberto Carlos's 1997 kick, the initial parameters were extreme. The ball left his foot with a forward velocity of 36.7 meters per second, paired with an angular velocity of 58 radians per second. This specific strike took place from a distance of 35 meters. Over that distance, atmospheric drag acted continuously on the ball, reducing its forward velocity by nearly a third. However, the friction of the air is not strong enough to significantly slow the ball's rotation, meaning the spin rate remained virtually constant. Looking at the spin number equation, as the forward velocity in the denominator shrinks, the total spin number grows. This increasing ratio causes the trajectory's curvature to tighten as the ball travels. While a shot from 20 meters would have followed a simple circular arc and missed the target, the 35-meter range allowed enough flight time for the velocity to decay and the spiral to tighten. That extra distance was the physical requirement for the ball to hook back on target. The physics invert when a ball is struck perfectly through its center of mass, transferring immense power but near zero spin. Without rotation, the stabilizing Magnus effect is completely neutralized. Instead of a smooth, asymmetric flow, the non-spinning ball experiences a phenomenon called von Karman vortex shedding. The fluid flow breaks off the rear of the bluff body, forming alternating, chaotic swirls in the wake. Every time a vortex detaches from one side, it exerts an equal and opposite force on the ball. This asymmetric shedding generates a fluctuating lateral lift force, pushing the projectile erratically left and right. This specific aerodynamic instability is quantified by the Strawhole number. In a knuckleball, the chaotic motion operates on a low-frequency mode, causing the ball to wobble laterally about 3.5 times per second. Because the ball is moving at high speed with no rotation, microscopic geometric details become critical. A stitched seam or air valve acts as a mechanical tripwire, forcing the incoming air to separate unevenly and exacerbating the chaotic lateral forces. A knuckleball is essentially a projectile stripped of aerodynamic stability. It surrenders its flight path to the stochastic, random fluctuations of its own fluid wake. Players manipulate trajectory using speed and spin, but engineers dictate flight through the physical topology of the ball's surface. At lower speeds, the boundary layer of air surrounding the ball is laminar, separating early and creating a large wake that pulls the ball backward. At higher speeds, this layer becomes turbulent. A turbulent boundary layer carries more energy and clings tightly to the surface further toward the rear, resulting in a much narrower wake. The exact moment the boundary layer shifts from laminar to turbulent is called the drag crisis. When this transition occurs, the overall drag coefficient on the ball plummets abruptly. This chart shows the drag coefficient of several World Cup match balls plotted against their Reynolds number, which corresponds to flow speed. You can see steep vertical drops where the drag coefficient falls rapidly as speed increases. The precise speed at which a ball hits this drag crisis is dictated by its physical roughness. A rougher surface trips the air into turbulence sooner, meaning the ball enters a low drag state at a lower speed. This dynamic explains the infamous performance of the 2010 Adidas Jabulani. Engineers reduced the panel count to 8 and utilized exceptionally short, shallow seams. By looking back at the drag data, the Jabulani's lack of surface roughness delayed the turbulent transition. This pushed the ball's drag crisis to an unusually high critical speed of roughly 27 meters per second. When struck at typical free kick speeds, the Jabulani started its flight in the low-drag turbulent regime. But as it traveled and decelerated, it crossed back under that high critical threshold midair. The ball suffered a reverse drag crisis, causing the drag coefficient to instantly spike, which abruptly slowed the ball down and induced massive wobble. Modern engineering corrects this error. The 2026 Triunda uses only 4 panels, but features deep, pronounced macro grooves and dense surface texturing. This engineered macro roughness guarantees the boundary layer trips into turbulence at a much lower speed. The ball remains in a stable, low-drag state through the entirety of a standard flight, decelerating predictably. The trajectory of a soccer ball is a continuous negotiation between the kinetic vectors applied by the player and the aerodynamic topology engineered into the surface. A high spin strike from a distance exploits the mathematics of drag decay, isolating the Magnus effect to bend the flight path into an exponential spiral. A high power strike with zero spin deliberately removes that stability, forcing the ball to ride the chaotic, oscillating lift forces of asymmetric vortex shedding. Both trajectories ultimately depend on the physical state of the boundary layer and precisely where that thin sheet of air separates from the sphere. These trajectories emerge when biomechanical precision meets aerodynamic engineering. By controlling the boundary layer, players and engineers transform the stadium into a laboratory for fluid dynamics.